Hi everyone, I'm Raja. I'm doing my master's in computer science, and then basically in this talk I'll be presenting about our work on titled "No More Strided Convolutions or Pooling: A New Building Block for Low Resolution Images and Small Objects." So this work is done along with Tai Leo. Our paper can be found in using the QR code, and then all our code is on GitHub repository. So the outline of this talk is, first I'll be talking about what is the motivation behind our work, and then next thing is what are the key observations, and also our new building block called SPD-Conv, and then use how to use our SPD-Conv in two computer vision representative tasks like image classification and object detection, and then we'll be going over training and then experiments and conclusion. So the motivation of our work is, we all know that the CNN classification accuracy drops significantly when we train and then test it on low resolution images. And then the second motivation is the object detection models suffer large MAP loss on small objects. So like when we look at state-of-the-art architectures like YOLO V5 and efficient DET, so we see that there is a large gap between AP that is computed on large objects with AP that is computed on small objects. And then the right bottom figure, if you see, the mask RCNN model basically failed to detect this extremely small objects like these birds. And then like the key observations that lead to build a new CNN blog are the usage of the strided convolutions and the pooling basically sacrifices the feature map granularity when we do the downsampling. And then the second observation is, in most of the common settings of CNN architectures where we use 3x3 kernel with stride equal to 2, there is an asymmetric sampling between even and odd rows or columns, and then that results in a biased feature learning. And also say that we use a 2x2 filter with the stride equal to 2, then every pixel in feature map is sampled only one time, and then that can lead object detection models not to detect the very small objects. So these two are the key observations, and then so that is the reason why like we built a new building block called SPD-Conv. Basically this, we wanted to eliminate the usage of strided convolutions and pooling and then replace with our building block called SPD-Conv. So our SPD-Conv basically comprises of a space to depth layer and followed by a non-strided convolutional layer. So space to depth is basically, it is proposed before to the transform a raw image. Basically, let's say that we have a 3-channel image of resolution height by width. So we store all this information along the channel dimension by reducing the image size. But in our method, we use that to downsample, like we use the same idea to downsample in a feature map. So let's say that we have a feature map of resolution S by C1 number of channels. So after applying SPD layer, we bring down the spatial resolution to S by scale, but increasing the channel dimension by a factor of scale over 2. So after that, we apply a non-strided convolutional layer with filter size of 3x3 and stride equal to 1. So this is the building block in a pictorial way. So let's say that we wanted to reduce a feature map resolution of S by S of C1 into S by 2 by S by 2 by C2. So we apply space to depth transformation to get 4 feature maps. After that, we concatenate these 4 feature maps along the channel dimension. And then in the next step, we apply a convolutional filter of size 3x3 and then stride equal to 1. So this is the the architecture for our block, and then this block is used to reduce spatial resolution by a factor of 2. And then to use our SPD-Conv, so let's say that we wanted to use it in object detection models. So we took YOLO v5 architecture, the state-of-the-art architecture, and replaced all the stride-to convolutions with our SPD-Conv block. Similarly, for image classification, we took the ResNet18 and ResNet50 architecture, and we replaced all the stride-to convolutions with the SPD-Conv block. So this is the detailed architecture after replacing the stride-to convolutions with SPD layer. So the YOLO v5 architecture consists of 5 stride-to convolutions in the backbone and then 2 stride-to convolutions in the neck architecture. So we replace the stride-to convolutions with our SPD and then Conv block. So this is the architecture obtained after incorporating our block. Similarly, we take ResNet18 and ResNet50 architecture, and we replace the stride-to convolutions with SPD-Conv block. So in the ResNet, so in the skip connections as well, there are stride-to convolutions. So we replace with the SPD-Conv in the skip connections as well. So these are the this is the training setup. So we follow a standard training setup for object detection. Like we use the COCO 2017 dataset that is containing 118K training images and 5K validation images and 40K test images. And then for hyperparameters, we directly adopted from YOLO v5 paper, YOLO v5 repository without retuning. And to compute the evaluation metric, we use both validation and then test set and the different IOE thresholds and also different object scales, small, medium, and large. So like similarly, YOLO v5 had like it's 4 scale of models: nano, small model, medium model, and large models. So we also use the same depth factor and width factor to obtain YOLO v5 SPD in S and M and L. So if you look at these plots in the bottom, so we see that we using the SPD block, so we outperform both APS. We outperform nano, small, and medium models on APS. Similarly, when we compute APS on large scale models, our approach of using SPD outperforms the state-of-the-art architectures. And then these are all the results that are evaluated on validation dataset and test dataset. If you look at the performance on APS, so there is a consistent improvement of like approximately 13% on the nano model, and then 11% on small model, and 8.6 on medium, and then 1.8 on large model. So there is a consistent improvement on APS. And also similarly, the same is observed on the test dataset as well. There is a consistent improvement of accuracy on AP small. Then these are some of the visual results. So if you look at this, the left top figure, so here these are the predictions made by the YOLO v5 model, and the right one is a prediction made by YOLO v5 with SPD block. If you see that this occluded giraffe is missed by YOLO v5 M prediction, but with SPD we are able to detect the object. Similarly, in the bottom 2 figures, so there is a face that is not detected by YOLO v5, and also 2 bench objects here. Similarly, for image classification training, we took the low resolution images like tiny ImageNet dataset that is containing 500 training, 50 validation, and 50 test for each class. And we also took CFA 10 dataset containing 50 10,000 training and 10,000 test images. And then for tuning the hyperparameters, we use random search approach, and then the learning rate decay is directly adopted from ResNet paper. So similarly, on the image classification, we see the improvement in accuracy. So ResNet 18, after replacing with our SPD block, was able to have a good improvement in accuracy. Similarly, the ResNet 50 SPD on CFAR 10 has a improvement in accuracy. So these are the visual results on the image classification task. So these are 8 images that are misclassified by ResNet 18 model, but they are correctly classified by ResNet 18 SPD model. So basically this is the true label, the green one, and then the blue one is the prediction that is made by ResNet 18 SPD, and then the red one is the prediction made by ResNet 18 architecture. So to conclude our work, so we basically identified a defective and yet common design in CNN architecture, that is the usage of sided convolutions and pooling. And to eliminate that, we proposed a new building block called SPD-Conv to replace them. And we do downsampling feature maps while retaining all the granularity of feature maps. And our proposed approach is a generic and unified, that it can be applicable to any CNN architectures where we use sided convolutions or pooling. And we showed its superior performance on 2 computer vision tasks like object detection and image classification. Yeah, thanks. That's all.
Thanks for the presentation. There is one question in the audience.
Hello. So, have you tested your convolution for regression in the average precision of actual big objects?
On big objects?
Yeah, is there a regression of the metrics for the big objects? Because you apparently improved a lot the small objects detection, but...
Yes, so when we tested on the large objects, APL as well, the performance has improved a bit.
Yes, improved as well. Nice.
Yeah, thank you for the presentation.